All right. Morning. Let's go ahead and get started, I guess. So, might be relatively quick today. There's kind of one main thing I was gonna go over, which was there wasn't a whole lot in the lecture notebooks about the last part of the current assignment. So I thought I'd talk a little bit more about that. I only kind of touched on that briefly last time. So I should bring up the textbook too. So. Second here. Grab that real quick. All right. So anyway, just for people tuning into this, so usual kind of reminders. Yeah, I'm looking for the assignment 5. I didn't get back to the assignment 4. Sorry it took so long. Still a bit behind. I'll try not to be quite so long on the next assignment 5. So hopefully everybody's made good progress on that. But yeah, reminder that I'm looking for that tomorrow. So that's Friday the 11th. Our assignment on the decision trees and the ensembles. I'll look at kind of a little bit of this idea of stacking here. In case anybody needs more information about it. So, looking ahead, I keep mentioning this. So we are our last 3 or 4 weeks is kind of a new topic. Should be interesting. So up to this point, we've been, concentrating on what's known as supervised learning. So that's the idea where you have a data set and it's labeled. And then we've looked at various machine learning algorithms that can create a model, so they can take the inputs and have a model that will make predictions what the output would be, whether the output is some sort of a discrete value in terms of classification, like yes, no, or true, false, or whether it's a regression where we're trying to predict like a house price based on information about housing data that are for sale, that kind of thing, right? So, we spend most of the time on purpose on that because supervised learning really is the majority of stuff. When you'll see people applying machine learning out in the wild, they're usually doing supervised learning. But the unsupervised learning methods we're going to look at next week are they're very useful. Of course, that's why we want to at least mention those, talk about those. So we're going to basically look at clustering. Two types of unsupervised learning. So this idea of clustering data, and then this idea of dimensionality reduction. So where you take something that's high dimensional and you kind of reduce that. You kind of represent that in a lower dimensional space. So both of those are very useful things that can be done for exploration of data sets and also for cleaning or for creating sort of new features for data sets as sort of a precursor to doing supervised learning. So anyway, so look at that. So we'll be doing a shift on that. I'll bring the textbook back up. Today we're finishing up. I'm going to probably just jump right to the boosting and stacking here on ensemble learning, since I didn't have a lot in our lecture notebooks on that. And then we're basically looking at dimensionality, chapters 8 and 9 for the remaining 3 or so weeks here, from our official textbook. So let me take a moment. Let me open back up since I didn't have a whole lot in the lecture notebooks, let me just go ahead and open up the assignment again. We'll jump into that. So as usual, I've been having a few people, so I know people are working on the current assignment, asking some questions, so keep asking those. Send me an email if you need office hours today. If you see this, I've got something that's going to be going on during then, so I'm not certain whether I'll be available in there or not. So. So let me get my assignment open here. So we are just a reminder about assignments. So after we finish this one up, there is one more assignment on unsupervised learning, assignment 6, and we still have our remaining test 2, which we'll hold during the actual last week of classes. And you should be working on your class project. I didn't mention that. I still wanted to try and look at that and maybe give a little bit of feedback, so I still haven't been able to get and do that, but do keep that in mind, keep trying to make progress on that. Part of probably a little bit of my evaluation will be that there was some evidence that you were doing stuff, each week or something like that would be a good idea. So. And let me know if people. So we are getting down to kind of where you should be. Have some ideas on that and have done some work on it. So if you do want to talk about that, let me know. I'll be happy to talk about people's class projects if they want some ideas or suggestions, or want me to look in particular at what they're doing right now a little bit closer. In the last couple of weeks while you're working on it. All right, let's get that reopened. Okay, so I got my project back up again. I'm just going to open up my assignment notebook again. And I'll jump right back down to the task 5 and 6. So for the rest of today, I think I'm mostly talking about the stacking stuff, just to make certain that people kind of have an idea of what we're doing here. So I sometimes I might be saying some of this stuff a little bit. Our textbook refers to that as a blender, but it's under the stacking section here. So anyway, the last two tasks are basically about that. So I thought I'd bring up this figure here. This is kind of what I have in mind for the last one. Okay, so the idea for the last task is we're going to be creating multiple different types of estimators to do predictions on the same data set. So we're still using the Magic Telescope data set for the assignment 5 here. So, and in fact, I asked you to reuse the work that you did on the previous task here. So you should be using the same the same estimators that were done when you created your function for the task 3. So your task 3 voting ensemble is supposed to create and return an ensemble. So it returns one of these voting classifiers, but inside of that ensemble you should have created it to have the 5 estimators that we talked about here. K nearest neighbors, decision tree, logistic regression, support vector classifier, and a multi-level perceptron. So hopefully, we've kind of covered all those except for the multi-level perceptron in this class, which is a neural network. But we have looked at briefly K nearest neighbors. We looked at decision trees, logistic regression, and support vector machine. So all the first 4 should be familiar, right? So the idea going back to this, if we were to update our figure for what we're doing for the last 2 tasks, is we're going to have 5 estimators fitted to our data set, but then instead of using the scikit-learn's, its class, what it was called, the voting classifier, in order to combine the output predictions into using like a vote. Okay, so what's being shown here on the blender, I have to remember our textbook here, so it might be using blending in the sense that this figure is kind of implying that we're doing a regression problem here. So the predictors or the estimators, the individual ones that we have here, are outputting like a real valued number. So for our Magic Telescope data for assignment 5, they're outputting just a binary result, 0 or 1. Or in fact, so people online won't be able to see this, but in fact what we're going to be using for the task 6 is we actually want to output the predicted probability. So like for our test or train data 1, we might have, say, like a 0.7 that it's true, or whatever I can't remember what we were doing for the Magic Telescope data, but it was a binary classification, so yes, no. So, and 0.3 for the false. So we're actually going to be using, so we might have 0.6, 0.4, so on to our inf training input. Maybe it's 0.01 and 0.99 or whatever. So we're actually going to be using the output, the confidence, as inputs to what's specified as the blender here. Okay, so and in our case though, right? So the blender, then we're going to be training just another estimator. Okay, so I need to read the instructions myself. I think I left it a little bit open-ended, but you can choose something. Some kind of classifier like we've been using, support vector classifier or decision tree or something, to be the blender. And so we need to train it basically on, we're gonna, once we train the individual estimators as a first step in our stack, so it's the name stack here I think comes from the idea that we're stacking some sequence of estimators together here. So once we train the first level of our estimators, we will get the outputs on a different data set. So we really need to split the data set into 3 parts. I discussed that briefly, but that's one of the first methods that you do on the assignment 5. So we really need train, test, and validation data here. So we're going to be using the train data in order to output this set here. And then this data, the output from we'll use the train data to train the estimators here. But then in order to generate the data set, we're going to use to train the second level of the stack here, the blender that's labeled here. We need a different data set. So we will generate and stack this data using the validation data set. Hopefully I have that right from my memory here. So we will, after we train these, we'll use the validation set to get this output from each one of these, and we need to stack that together. So this will become input. We'll have 5 sets of outputs from our validation data. So our validation data here, we'll have outputs. We'll have 5 outputs since we have 5 estimators on this level. Each one of them is outputting basically 2 results: the probability that it's yes or the probability that it's no. So we'll actually have 10 features as inputs coming into the thing we're going to use to blend the results together. Okay. Hopefully that makes sense. So that data we'll use to train one more estimator. So given these inputs, it needs to predict, we're still doing classification, so it will still need to predict true, false, yes, no as the output, the final output here. Okay? So that's really all there is to stacking. And you can imagine kind of carrying on that idea. So I don't know if anybody's ever found it useful to have even more levels than that, but you could potentially keep doing that idea. So have multiple things that you blend together from the first level. There's probably pretty quick diminishing returns. So it probably doesn't help very much, I'm sure, in practice, much more than just having one level. But the idea is that, so we're doing something more sophisticated than just a straight up vote, majority vote, or the slightly more sophisticated that we did with the soft voting, where it's a majority weighted vote, where we take into account how confident the individuals were, but combine that as like a weighted average of somehow. It's kind of how the soft voting worked here. So what we're doing here is we're training a new estimator on this data's input. So we have to have all of this, plus of course we still have the correct label. So once we generate this output data from our validation data set, we can feed that in. So we know what the outputs were from these, and we know what the expected answer should be for each one of these. So it just becomes another estimator problem. So the idea is that some of our estimators on the first level here, some of our predictors, might be better at certain parts of the data set than others, right? And in fact, if you read, the description here, we could even do that kind of explicitly. We didn't really do that in this assignment, but we could even split our training set into different subsets to train the individual estimators. So we are, for our assignment, we're using predictors on the first level that are non-homogeneous, but we could have done the same sort of thing like is done for a random forest. We could have just used a bunch of decision trees and tried to make them different, non-homogeneous, by doing the same sort of tricks that we do for decision trees in a random forest, like split up our training set into different subsets by samples, or maybe even split them up by features or something like that. But for this assignment, we're really we're not really exactly doing like shown here on the figure 13. We're using the whole training set. We're not splitting it up into subsets. We're getting kind of some differences in the population by using different sorts of estimators on our first level. So we'll support vector, classifier, and decision tree, and those 5 that we're using in our assignment here. So I'd kind of forgotten that the very last thing, it even kind of discusses that idea of a multi-layer stacking ensemble. So I've never done that in practice, so I don't know how often it would be useful to keep extending that basic idea, but you could certainly keep doing that. So anyway. So back to the assignment. So that's basically what we're doing here for the last 2 tasks. If people had questions on that. So the first, you are going to be reusing the function from task 3. So the way that the individual classifiers on the first level are created is just by reusing the task 3 function that you had to create a voting classifier with those 5 estimators as part of the voting ensemble, right? But then once we do that, we're not going to actually be using the voting ensemble, so we're not going to be doing hard or soft voting. We're going to just be using those as individual trained classifiers and doing a stack by hand. So and we do have to do this. So scikit-learn doesn't have a class to do this kind of stacking for you, like is described in the textbook. So we don't have like we have the voting ensemble that we're using for the voting classifier we're using for task 3 here. There's no like stacking classifier in scikit-learn because this isn't as common of a thing that's done here. So we have to sort of, if we're going to do the stacking, we have to do it by hand basically. So just to look at the first task here, so the purpose of this first one, the create stack data, so notice that we pass in the voting classifier and the training data. So at this point in the assignment, it's expecting that it's already been split into 3 parts: training, validation, and test. Okay. So so here, so actually, we expect a voting classifier passed in that has already been set up to have the individual estimators that we're going to be using as the first level for the stack. So that's what's coming in as the first parameter for this function. And then the second one, so you'll see later on, so when we do these first tests of this data, we test it by passing in the training data again. But later on, the way that we're going to actually be using it is you're going to be passing in the validation data. So let me just go through the kind of the details of this. So for the first one, what needs to happen is if we pass it in, the set of estimators with the training data. So we give not really pseudocode here, but kind of an idea of how you should implement the create stack data. So you do need to iterate over each of the estimators and the voting ensemble you're given inside the function. You assume that's already trained. So this VC, we're assuming that the voting classifier was already created, and we fit it to a set of data here. Okay? So so you're supposed to have it that you're supposed to use the predict probability method. Okay? So use the method that will give you the confidence or the probability predictions for the input data that you're given here as output. And so in this case, as is shown here, each estimator, the training data that we give you here has 5,000 samples, so there should be 2 outputs for each of the 5. And then to stack the data, you have to combine each of those 5,000 by 2, so 5,000 rows by 2 column shaped data into a resulting set of data. So you should end up with something for this first test that's shaped 5,000 by 10 columns, right? So we've got 2 columns for each of the 5 estimators in the voting classifier that's passed in. So you end up with 10 columns in the X stack that's returned here. Okay? So there's lots of ways you could do that, but yeah, I do recommend that you use look up some methods from from NumPy for combining together arrays here. So, we are expecting, give me a second here, so I just want to check, but we are expecting using NumPy arrays here. So let me just make certain that's true, though. So if we look at the tests for the task 5, so I guess we are expecting it to be like a pandas data frame probably coming in here, or we're maybe a bit agnostic here. I'd have to maybe go and remember exactly, but looking at the tests, so you can kind of see some of the stuff that we're doing when we test your part 5 here. So we are reusing your train validation test split on and we're using your load data to get the actual data out of the file and splitting it with your train validation test split that you should have created in the first 2 tasks here. And also reusing your task 3 one to create the voting ensemble that should have the 5 different classifiers in there, and then from that, so this is all set up. So all of the actual tests are using these values that are defined here, the X train, Y train, and then also the VC. So then we just call your data set with the validation data, or with some random data that we generate at random to try different things here. So yeah, I mean, looking at this, probably it should be a pandas data frame that comes in But on return, it maybe needs to be a NumPy array for the all close to work here. I have to check that. I can't remember exactly whether it'll work if you return back a pandas data frame or. But yeah, since you're getting a pandas data frame coming in here, you might need to first change it into like a NumPy array so that you can easily combine those together into the resulting stacks of data that's returned back from there. So, and I don't think it's tested on the return though. Although again, I'm not certain if this might not work unless the thing that you return is a NumPy array. So I don't think the all close works on pandas array. So it looks like we are expecting NumPy arrays coming back from this. So. But yeah, I don't know. I haven't had questions on that. I have to go back and kind of remember that. But you might have to try that different ways. So you might have to play around a little bit with whether you're convert it back into a pandas array before you return the result there, or leave it as a NumPy array to get everything to work at least the way the tests are written. So. Okay, but conceptually, that's the idea. So that is really just doing the stacking of the data here. And again, we're basically going to be reusing that for task 6 here. So on task 6, you're supposed to actually create the stack and use it. So what's expected to be returned back from the final method that you create. So you pass in a set of data that you're going to be used to train the estimators at the first level, but then you also need to pass in a different set of data that you can use to stack together that you use to train the final blending estimator. So the blending estimator is supposed to be that class that ends up at the top of the stack here when you're working on this final task here. So so you should be, and I'll be looking for this, but you should be reusing most all your functions that we used before. So you need to reuse the task 3 function to create the voting ensemble. You need to do that and have it fit on the training data, right? So the first 2 pandas or NumPy arrays that come in are what you're going to be training the individual base level estimators on inside of the voting ensemble there. And then reuse the method you just did on task 5 to stack the predictions of each of those estimators into a new resulting array. This one here, so be careful about this. You won't be able to get this to work right unless, so when you do this step 2, on the last one, you need to be doing that on the validation data, okay? So I don't know if I was clear on why that's the case, but so there would be leakage. So if we just recreated a set of data to train the next in the hierarchy that was reusing the data that we fit the first base level estimators with, there's a potential that we would be leaking information to our final result here. So that's because we want the data that we train this on here to be from predictions that these weren't trained with. So if we didn't do that, we would risk having something that was badly overfitting on the data that we use for the initial training, and it would be much tougher to detect it if we did it that way. Okay, so I don't know if that's a good description of why we do that, but it is necessary to use a different set of data to create the blender, to create the one at the top of the hierarchy. Okay? So, and that is mentioned kind of in the pseudocode or the steps for task 6 here. So make certain that you are creating the stack data from the validation data set. I guess I did specify, so I did ask you to use another support vector classifier, so your blending estimator should be an SVC, a support vector classifier here. It should be trained on the validation data, and that's the thing that's returned as the blending estimator, the first return tuple from our function here. And then here at the end, I do ask you to by hand kind of evaluate the accuracy. So again, since we trained the base estimators using the training data set, and since we train the blender using the validation data set, the accuracy that it gets overall using those is not going to be, we shouldn't trust it in terms of how well this would be representative of how it does on unseen data, okay? Because it could have been overfit on either or both of those data sets, since those were using the training at one level or the other, right? But that's kind of the first thing you should do. The way to do that is you kind of by hand have to create. So, for example, you have to create. For convenience, you really should be reusing your functions to do these things. But like to do the evaluation, the accuracy on the training data set, you would first have to create the stack data from your ensemble from the base methods on the training data set to get outputs from those. And then the outputs from that, you should use the final blending estimator to give you the predictions, right, from the stack training data. And from that, you should be able to calculate how accurate it was on the training data. And then you do the same thing to report the accuracy on the validation set. So create the stack data on the validation data sets, and then from those you have to feed that into to get the final predictions from the blending estimator that you have, and calculate the accuracy on those. But like I said here, I mean, those aren't necessarily very fair estimates of the performance. So there is a third data set that should not have been used at all in this assignment. So we use the test, or so we use the train and the validation, but we haven't used the test data set yet. So So yeah, I mean, all three of these should be the same kind of thing. Just make certain you use it on the right data set. So reporting the accuracy on the training, the validation, and then finally the accuracy that you get on the completely held back final test data set here. So, and kind of as a final thing, though, I do ask you to also show the confusion matrix and report an ROC curve for the performance here. So since we are doing classification, accuracy isn't necessarily a good kind of measure of how well it's doing. You kind of want to really look at the confusion matrix and some of those precision and recall, some of those things that we talked about, or the ROC curve. And it might be useful. So the kind of the most fair. So you can compare this to the performance that you got for the task 4 and the task 3, like the hard and the soft voting in task 3, and the task 4 where we did where we should have done like a random forest of some kind. So. So here I gave this caveat before. You might not see. I think that if you do everything right, you shouldn't see any worse performance than you had on the task 3 and the task 4, like accuracy. But you might not see much of an improvement. So I think what usually, just to kind of calibrate your expectations, usually the random forest does get a little bit of a performance boost over the hard and the soft voting, I believe, on this assignment using the magic telescope data. But this final stack it's usually about the same as the best that you got, which is usually your random forest or your extra trees from task 4. So probably won't improve, but it hopefully should be at least about the same. So, but I could be a little bit off on that, on my memory of that. So you shouldn't. I'm saying that you shouldn't worry too much if it's getting about the same, but just a little bit below. There's some randomness in this as well. So, although if it's significantly less, or if any of these are significantly different, there might be an issue. So that would be something that you might need to just be aware of or ask me about if you're working on this. So. Okay, like I said, we still have a little bit of time, but that was I think, everything I wanted to mostly talk about on the last 2 tasks for the assignment here. So, I'm just kind of looking to see if some other stuff that I wanted to mention. There was one, I don't think that I kind of mentioned feature importance. I think it was in the lecture notebook a little bit in there. Just kind of as a final thing, because I would like to mention this in class. Another useful thing for random forests, if I didn't talk about it, is they can be useful for determining which of the features are more or less important for like a classification or a regression task. The basic idea is that because of the way that decision trees work, the feature that gets selected to be at the top of the tree for the first split or the first couple of splits usually are the ones that give you the most gain in terms of reducing the mixing, that impurity that we talked about, right? So by training a random forest in the normal way, and then by determining when the feature, how high at random, how high usually it ended up in the tree, you can get an estimate of how important each feature is. Okay, so that could be another useful thing when you're doing data exploration, right? So that's often kind of a question you should be asking when you're exploring a data set is, okay, I have these features, are some of them going to be more important than others to do my task if I want to do a classification or a regression task? And you can use this for either one, classification or regression, to estimate the importance of features here. There are other things in the scikit-learn library that you can use that are explicitly for estimating feature importance, but this is a pretty easy, quick way to do it. Use a random forest. It's built in. So one of the one of the attributes of a trained random forest, this feature importance, will actually give that to you. So it's actually just it's like you end up with an array of each feature name and its importance. So kind of an estimate. So that, I think that those are supposed to add up to 1 if you add those all up. And the higher, the more the more important was. The more often it appeared near the top or at the top of the decision trees that were used in the random forest that were created there. So by this example from the textbook, when it did it, the petal length, the petal measurements were much more important than the sepal measurements as features that could be used to create classifiers for the iris data set that we've used quite a bit in the class there. So from that kind of information, sometimes you can try building classifiers where you don't use, and so you can maybe cut off, and sometimes you can get better performance, or you can get the same performance, but with a lot less need to train stuff by only using like the top 50% of the features or something like that if you have a truly big data set. All right. I'm going to go ahead and wrap up there. So I don't have any other kind of things looking through this that I kind of want to bring up. So, yep, that's it for today. Get the assignment 5s in. Let me know if people have questions on that. You still have, today and tomorrow to get it in before the official due date. So, all right, let's go ahead and end there.